Three. All right. Newton has three laws. That's good. What are they? That's the hard question, right? What's Newton's second law in particular? F equals ma, right? So force equals, and I gotta be careful about that. Force equals m. I'm gonna write it this way: dv by dt. All right, I use a calculus way of writing that. Now I gotta be careful. That's not just any force, right? What is that? The sum of the forces. That's the net force. All right, the net force. Now my way of thinking about that, here's my, this is my block. All right, and my block has a mass m. All right, now let's say that this block is pulled forward. So there would be a force pull, I guess, on this guy. All right, so I pull it forward. Again, we're talking about electromechanical systems, so I got to get to the mechanical piece. Electro, you guys are used to thinking about mechanical. I got to think about that part too, right? So there's a force of pull on this thing. Now my block is sitting on a surface. So what other force does this guy have to experience? Friction, yeah. And there's vertical forces too, but I'm worried about assuming it's just a one-dimensional motion. So there's a force of friction. Now, why did I push that going? It opposes, right? It's a resistive force, and you can get formulas for it or what have you. But if I were to try to figure out here how I can, so this Newton's law is the sum of those forces. All right, so how do I write that here? The force of the pulling minus the force of the friction is F net. Like that. Okay. And I have pull in the positive direction and friction in the negative direction, because if I look at it, I don't know, you tell me, if I look at it this way, and the net force equals dv by dt, me pulling it does what to the velocity, to the speed of it? Increases it, right? And the friction does what? Slows it down, right? So it should be in a negative direction. Now, if I'm moving at a constant speed, so imagine this guy's a car, right? So the force of pull would somehow be coming from the car's engine, right? So if that's the case, and I'm moving at a constant speed, right? So if I'm moving at a constant speed, what's true about dv by dt if I'm moving at a constant speed? What's zero? The acceleration is zero, right? So if v is constant, so v equals a constant, right? So if I'm moving down the road at essentially 55 miles an hour or 60 miles an hour or whatever, and it's constant, then this guy here is equal to zero. So what does that mean? The net force is zero. So it means whatever force I'm pulling with is exactly equal to the force of friction. All right, and that's a basic principle by which a motor works. This is the part people can easily think about. Linear motion is nice and simple to think about. We deal with motors, we have this setup though. All right, and this is a classic thing that I see. What am I looking at on the, there's I don't know, 4 things that I see in that picture. There's 2 unique things maybe. What do I have on the right side of that? What are these things? These are motors. Yeah, you've seen some, I guess, now. Right? So there's motors here, and what are these guys over here? Anybody know? Pumps. All right, these are pumps. All right, very common thing that I'm using a motor for, right? So basically, and I've got a coupling that basically links the motor to the pump, right? This guy is exactly like what I have in the previous image, right? So where does so in this case, we said there was the force of pull that caused it to sort of move forward. Where's that come from in this setup? So the pump's moving, right? I apply some current to this thing. There's the pump moves. Where's the force come from? Well, yeah, so it comes from the electrical side. Yeah, it comes from the energy source that I'm hooking this guy up to. And where's the force of friction come from? The water, right? This guy's pumping a fluid, right? So as that pump moves through the fluid, there's a friction against the pump, right? So if I tried to set this up internally, now I'm not talking about force now, right? Because the motor rotates. So if I'm talking about a rotational system, I have torque, right? So, all right, so force, in this case, I have torque, which I'm going to write with a T. All right, so T is torque. All right. Now, what other variable do I worry about? I worry about the angle of it, so theta. And then which is the angle. What's the other thing I worry about?
Angular frequency.
Angular frequency, yeah, which I write as omega, capital omega, like that. All right. So everybody's favorite, if I'm talking about the net torque, so you guys already told me if I'm in linear motion, I had the net force equals m times d speed by dt. All right, help me out with the net torque. If I have rotational motion, the net torque equals what times what? No. Force times distance sine the angle. Not quite. A torque does that, right? If I talk about, like, if I'm trying to open that door up over there, you know, and I apply a force at the door handle, the torque I compute is basically the force times the length that I'm applying it through. There you go. Moment of inertia times d speed by dt. Oh, all right. I'll buy you something in the vending machine when class is over as a reward. All right. I'm happy. Moment of inertia. All right. I write that with a J. Physics, sometimes they call it I. If you really go into some serious power system stuff, they'll call it H. I'm not sure what the history is behind that, but to be honest with you, they usually do a per unit moment of inertia. All right, good times. So torque net equals J times d omega by dt, where this guy J I call my moment of inertia. Moment of inertia. And, you know, there's ways to that comes from the mass, right? So if you can go back to your physics books to figure out how that's calculated, right? Moment of inertia. We're not going to get into doing a lot of calculations of that stuff. I might give you one sort of simple problem on it, but we need to understand this piece, all right? What's that? If I had that pump scenario, right? What I would say is that the motor exerts a torque. So this would be the torque of the motor, let's say, that tries to move this guy forward. If I hook it up to a pump, what's the pump trying to do? Stop it, right? So the pump would basically go like this in the opposite direction. And that means that the motor tries to speed it up and the pump tries to slow it down, all right? So I get that basic relationship. Comes down to it, this is what I need, Newton's laws of motion. The net torque is J times d omega dt. The net force is mass times dv by dt. Okay. Now, in problem 4 on the homework, you have a force problem, which we'll get to. And in that case, you've got a device that's trying to pick something up. So the force, if it's trying to pick something up, what's the thing that's trying to make it go down? Gravity. All right. So how would I figure that out? M times G, right? So so we'll get to that in a little bit, but so it's the same basic principle there. I'm trying to lift something up, so it has to overcome the force of gravity to be able to do it. Okay. All right. So these are all fun things to think about, right? As I got motors and pumps and stepper motors and cool stuff, but we got to start with the basic silly stuff first, which is so I'm going to draw my silly picture of my favorite C-core with a little gate of sorts hanging inside of it. Now, this device right here is something I would call a relay. All right. So what's a relay do? Everybody know what a relay is? Basically a switch. Yeah. So a relay is basically a switch, right? And so one place I use relays a lot is lighting, right? So if you go to the parking lot lights here, right, there is basically a sensor that says, hey, it's dark outside. And as soon as it says it's dark outside, that sensor basically sends a signal to a coil. And what that coil does is it's going to pull, it's going to do exactly like we were doing here. What it's going to do is it's going to pull that bar in, right? And what's that do? When it pulls it in, it probably closes some connection, just like a switch, right? So basically says, in the case of a relay, I basically have a switch that when I apply a current, basically pulls that switch closed. And the way you would pull it closed is by connecting basically the lever of the switch to that bar, right? So that bar will get yanked in and it'll close the switch. All right, so a motor contactor, a lighting contactor, that's the basic way it works. Or sometimes you have valves that work like this. All right, so the thing that I gave you in problem 4 in the homework is what I call a solenoid valve. Solenoid valve is basically just a valve that is got a coil like this. Basic electromagnetic motion, if I want to have one-dimensional motion like this, very simple way to make it happen. All right, and I want to figure out how much force this guy can produce. So when I put this little F right here, I'm basically saying this guy has the ability to produce a force. All right, which means he's got the ability to produce motion. So I want to figure out how to calculate what that force is going to be. Okay. Now the important thing is, as we're going to see, the magnetic force always acts to minimize the reluctance. All right, it acts to minimize the reluctance. So what it's going to do is it's going to try to make the reluctance in the circuit smaller. Okay, so Wusi, you look like you had a question. All right, gave up on it. All right, so I want to figure out the magnetic forces in this guy. All right, which means I want to basically create a magnetic circuit model. So let's take a look at what we know. If I give you a magnetic device of some kind, right? We basically say, well, I draw the magnetic circuit model for that thing. And what's in a magnetic circuit model? What are the elements in a magnetic circuit model? MMF. Yeah, I got an MMF. That's coming. What's an MMF? It's always a what times a what? Current times the number of turns, right? Is an MMF source, right? The flux I determined from the magnetic circuit model, right? So what variable do we use for that one? Flux. This is phi. Then we figure out the flux linkage. That's lambda. And then I get the inductance. How does that relate to lambda? L times I, right? And if I go one more step to voltage, if I'm trying to get an electric circuit model, I know V equals d lambda by dt, which is equal to what? V equals d lambda by dt. So if lambda is this, what's that equal to? Okay, so we've got two good answers there. So I saw J omega, that's if I have AC systems, right? Then I can do phasors. He just said L di dt, right? Is that right? You're questioning it. Hey, it should be, right? Yeah, that's part of it. L di dt plus I dl dt, right? Why did I write it that way? Because because L times I, both of those two things could be functions of time, right? In this picture that I drew right here, the magnetic circuit is going to change, isn't it? If this thing's going to move, if that piece is movable, then essentially that says the magnetic circuit can change. All right, so this is actually the more realistic thing. Now, when you're just dealing with an inductor, right, just a coil of wire wrapped around some piece of iron, L doesn't change. All right, but if I can have motion, that's a different story, right? Now the L can actually be a function of time. All right, so we're going to do that. And then to get to a force, what I got to do is I got to calculate the energy. Now, you guys learned a formula, which we're going to kind of derive a little bit today, that the stored energy, which I'm going to write with this, I'm going to write like this, the energy stored in the magnetic field. What's the variable W for? What is it? Work. All right, energy and work. So we use that because E is, we probably could use E, but E is often used for voltage in the context of magnetic stuff. So I use W to be energy, all right, or work. What's that equal to for an inductor? 1/2 Li squared. And that's not necessarily true, right? That's true for a pretty simple inductor, but not one that can saturate and all that kind of stuff. All right. So, but we're gonna if, under the right assumptions, that's at least true.
That'd be true for a lossless inductor. Wouldn't a loss?
If I had losses, then 1/2 Li squared is still the energy I store in it, but there's also an energy lost over time, right? That I would have to factor in. Well, the energy stored in it would still end up being this. But so good point. The energy I put into it and the energy I store in it wouldn't necessarily be equal to each other. All right. We'll get to something like that here in a second. All right. Anyway, bottom line is this process is not new. What's new is that I can get some motion while I'm going through it. All right. So let's start. I want to understand this guy. So I'm going to make this magnetic circuit model. All right. So in this case, what I've done is I've said the mu of the core here is infinite. And that's also true for this little movable piece. Sometimes call that the plunger, right? It can plunge in and out. All right, this guy's got mu equal to infinity as well. It's a lot easier for me to think about this problem if the mu's are infinite. What's it mean if the mu's are infinite in terms of my magnetic circuit model? The zero losses, there's zero reluctance to it. So there's basically zero losses in that sense, right? All right, so help me out. Help me draw the magnetic circuit model for this thing. Where do I start with the magnetic circuit model? My MMF source, which will be N times I. Okay. All right, now, which way does the flux go in this thing? Clockwise. All right, so my thumb goes in the direction of the current. My fingers curl around. It's going to go clockwise. All right. At least one part of one question on the exam is going to be tell me the direction of the flux, right? So just be prepared for that. All right. This guy's going to go like this. Going to go up. And it goes here and it goes around, always in a circle. All right. Now, where's all the action happening here in this magnetic circuit model? Over by that plunger, right? So I have a sort of a side view of that plunger. Now I want to say a couple of things. So basically, I guess I've defined kind of a coordinate system here, where I'm saying this is the x direction, right? Horizontally, and then vertically is my y direction. Okay. So I'm going to say that x equals 0 is right here. Okay, that's x equal to 0. Okay. So if I move to the right of that, x is positive. If I move to the left, x is negative. Okay. All right. So how do I draw the magnetic circuit model then? So what happens when I get to this area right here? Well, just imagine that it's stuck there in space. Okay, imagine X is whatever it is right now, right, in that picture. All right. Oh, I got some reluctances in parallel and series, probably, right? All right, so let's explode it. So I got two paths. All right, so Cody's saying I got two paths. One path is, I don't know what I'm going to call it, the big gap. Big gap. All right, where's the big gap? Big gap is here. Big gap. I missed. That's the big gap. All right, and then I have small gaps, right? Those small gaps basically are here and there. And notice they're pretty small, right? You may be looking at them saying, well, they're not even there. They're there, but they're small, right? So what's the parallel path? So let's be clear. All right, this guy goes like this. All right, closes up. What's the other path look like?
The reluctance of that piece.
Well, it's not just the reluctance of that piece. I'm going to say in that other path, I got three reluctances there. Right? What would it be? I have one going through the top gap. I'll call it RG. Then I have one going through the plunger itself. And then I have another one here, RG, like that. You guys with me? So basically, if I explode that view out for a second, and maybe make myself a little bit less space. All right. Basically, what I'm saying is this guy right here is RG. This guy is RG. This guy here has R plunger. And this space right here has reluctance of the big gap. You guys following that picture? Now, what did I say is true about the plunger? It's also got mu equal to infinity. So do I need that? No, I can get rid of that. That guy's going to be 0. All right. That guy's going to be 0. Now, what's going to be true? Let's write these out here. What's going to be true about the reluctance of the big gap and the reluctance R sub G of the little gap? The big gap is going to be a lot bigger. Now, why is that? Why would the reluctance of the big gap be a lot bigger? Because it's a lot bigger, right? It's length over mu times area. And the length of that guy is a lot bigger. All right. Let's say it this way. Let's say that as the way I've defined this guy, the plunger has a height h. I'm going to say h is much, much bigger than g. All right. So if I want to simplify that down, we had this picture here. This is big gap. This guy here, I'm going to say is 2 times the reluctance of the little gap, RG. Right, because those are in series with each other. Here's Ni. All right. So if, based on what you guys just said, R big gap, how does that relate to RG of the little gap? Yeah, they sort of have the same denominator. Our big gap's going to be much, much bigger. Or much, much bigger is a goofy statement, right? It just means much, much bigger than. You guys can ask about the area, right? Okay. Well, so the core reluctance I'm saying is 0. Because what I'm saying, so remember what's our formula for reluctance? Let's just remember that. R equals what over what? L over mu times the area. All right. I'm saying that both for all of the magnetic materials here, meaning that plunger, that movable piece, and the core, mu is infinite. So if mu is infinite, basically what I have is a magnetic version of a wire. The job of those magnetic materials is basically to direct the flux to where it's useful. It's useful in the gap. And now I've used that term useful before, and that probably didn't sounded weird. Now this is why I'm saying useful, because in the gap it makes forces. All right, and that's why, you know, there's always gaps in in electric machines, right? Because forces happen when I have gaps. All right, so I got to that picture. If our big gap is much bigger than RG, this is like saying I got 100 kiloohms in parallel with a kiloohm. If I had 100 kiloohms in parallel with a kiloohm, what's the combined resistance?
Basically, our big gap.
Opposite of that. It's basically a 1 kilo. It's basically the smaller of the two, right? If they're in series, it's the big one that matters, right? When they're in parallel, it's the little guy that takes over, right? So basically, that whole thing becomes this. So I took that weird looking device and turned it into that. All right, now, if I want to figure out what phi is, the flux would be coming out like that. So what's phi? Ni over 2 times the reluctance of the gap. Now we got to calculate what's the reluctance of the gap. All right. What is the reluctance of the gap? All right, so let me draw this picture over here. And we'll write out the reluctance on a different picture here. Okay. So this distance I'm saying here, this is x. This guy here has a height h. And the lengths of these gaps are each g. And this distance is d. And it's a length L into the page. All right, nice and variable on this. All right, so the only thing I care about is the gap, RG. So that's the length of the gap divided by mu times the area of the gap. So what's the length of the gap? So it's a length meaning if I have a field going this way, right? What's the length that's going through? For just one gap, it's G, right? For both of them, it's going to be 2G when I put them in series, right? What's the mu of the gap? Mu naught, because it's just air. What's the area of the gap? Well, yeah, so it would be its length times its width, right? So its length is L into the page. What's its width? D minus X. All right, the length is D minus X. Based on the way it's sitting right there, it looks like D over 2, yeah. But X can change ultimately. Okay, so that's the reluctance of the gap. All right, so when I go over to what I was doing here where I figured out the flux, I basically get that this guy becomes, N over the reluctance, mu, no, let's just write it. RG was G over mu naught L times D minus X. I flip RG over. So I have 2G mu naught L D minus X times I. All right. How do we get to lambda? N times phi. So this guy becomes N squared mu naught L D minus X over 2G times I. Now notice that thing I said earlier about if this thing's going to move, the inductance is basically this. This is L right here, right? L is a function of X. L is a function of position. And the position can change as a function of time, right? So L of X is N squared mu naught L d minus X over 2G. Now, one thing I'll say is why I'll give you a practice test. I like these symbolic type of problems because I can look at them and grade them a lot easier than when you guys put the wrong numbers into calculators and all that kind of stuff. So I like these sorts of problems. And I'll probably try to give you one like this on an exam. Okay. Because you spend all sorts of time putting numbers into calculators and you're going to calculate stuff wrong. Okay. This lets me see that it's right. Okay. All right. So now I want to use that to get to a force. I know what the L is. Somehow the thing that you should understand at this point, that's why I wanted to do the thing at the beginning, right? Is that there's going to be motion in this thing. All right. Now I want to figure out how to calculate it. So to calculate it, I have to do thermodynamics for a second. All right. So I've got a lossless device. It's a lossless energy storage system. It's a magnetic storage system. And in this case, what I have is two ports, just like I have in any motors. Okay, we're doing energy conversion finally now. So I got an electrical port here. And I got a mechanical port here. Mechanical. Okay. An electrical port on one side, a mechanical port on the other side. That means if I put electrical energy in, meaning I apply a voltage, I draw a current, I get a force and a change in position on the other side. All right, that's the basic idea. Now, what I want to do is I want to write out the first law of thermodynamics for this thing. All right, and it's an energy storage system. So we're doing big stuff in physics today. We did Newton's law, now we're going to do the first law of thermodynamics. What's the first law of thermodynamics?
That heat must transfer hot to cold.
You're saying it in a way that makes sense from a purely sort of mechanical standpoint. But if I just thinking about it, big picture.
High thermal energy is low.
Well, so thermal is only one way of thinking of it. Energy out plus losses equals energy in. Right? Basically, energy is neither created nor destroyed. All right. In a closed system, energy is neither created nor destroyed. All right. So the way I'm going to do this is in terms of rates, not energy, but the rate of energy. What's the rate of energy? What's the rate of energy? Power. Okay. So I'm going to say I got V times I. That's the electrical power going in. How does that relate to what's going out? Well, if I have a linear thing, you may remember force times position is equal to that. Well, if I'm talking about a rotational system, I'm not quite talking about a rotational system in this case, right? So I'm saying here, let's see. Be careful about this for a second. Yeah, force times X. Power plus there's one other place that energy goes, right? If this thing has a magnetic field, there is also energy stored in the field. Like that. All right. And I need to be careful about this. Force times the velocity is this would be a power. Force times the velocity is a power. Okay. So That basically is how's velocity relate to position? It's their derivative, right? So basically this is also force times dx by dt. So we can do some calculus here. So force times dx by dt. All right. Or in this case, I can write this guy instead of voltage. How does voltage relate to flux again? How does voltage relate to flux? It's what? How does voltage relate to flux? d lambda by dt. It's the rate of change of the flux linkage. Like that. All right. This is basically Newton's law here. So, or not Newton's law. This is the first law of thermo. First law of thermo. Theorem. Thermo. Okay. And I don't want to get too lost in all this, but if I got d by dt's in each of these terms, I can write this guy here as d lambda. So I times d lambda minus f times dx equals the rate of change of energy. So what did I do there? How did I get from there to there? I got a d by dt everywhere. All right, so you can write that in terms of the partials. Okay. This looks weird for a second, right? This basically came from the first law of thermodynamics, and I want to use it for a second. Now, if you took thermo, which everybody, I guess, does take thermo, right? You learned about state variables. You guys have to take thermo, don't you? No.
Study at one point, but I've not seen it any times.
Thermo 1 was required.
Not in degree where it's needed, but I could.
Well, there was a time when it was required. Well, there was a time when men were men, I guess, but the days have passed. Right? Perhaps, yeah. All right. So the energy is a function. Basically, there's a term we use called state variables, right? So in other words, that the energy stored in a device depends on its state variables. All right. So we don't need to get too lost in that. I mean, you kind of know this already, right? So basically, a state variable is to say, if I have a capacitor stores energy. The state variable is its charge. I put a charge onto a capacitor. That charge relates to the energy it stores. Okay. If the thing can move, in this case, what we're saying is the energy in this magnetic system depends on two things. It depends on its flux, and it depends on its position. All right. So what I wrote here, the energy is equal to I d lambda minus force dx. All right. So x, the position of the thing, and the lambda, if I know those two things, I can figure out its energy. So you get into all this stuff about conservations, and I don't want to get too lost in the details of this thing, because we can get lost pretty quick. All right, I want to jump primarily to the result of it. If I look at this here, I have a little bit of an issue. I do sort of a fancy sort of thing here, right? If I have a linear material, all right, what do I mean by a linear material? All right, a magnetically linear material is one where I have lambda equals Li. Well, that's what we've had all along. All right. If I had a magnetically nonlinear material, what does that mean? Well, it means that if I put more current into it, it saturates. And we've talked about that, right? But we're going to forget that. We're going to assume that our materials operate only in this kind of linear region. If lambda equals Li, if I have lambda versus I, it's linear, it's a line, right? So I can draw it like that. Now, here's the tricky part for this thing. What I just said is this is how I calculate energy. So I have this guy here. D energy dt is I d lambda minus force dx. Okay, now, if I have a regular inductor, nothing can move. X doesn't change, right? That gets rid of this piece, right, for a second. If I just had a regular old inductor, right? So in other words, if this guy didn't have his little movable piece, right? If it was just fixed in space, couldn't move, then I simply would have that this piece right here was gone. All right. Now, if I tried to calculate the energy, that tells me that so I'd have to do it by integrating both sides, right? If I integrate both sides, that would be I times d lambda. All right, now here's what's tricky about that. Usually we think, how do we get lambda typically? This is where I got to stop because I'm starting to get really mathy here. How do you guys calculate lambda? You put a current into something and you get a lambda, right? This is saying I have a current and I'm integrating with respect to lambda. So real quick, if I think about this in the world of calculus, this statement right here is an area in this curve or in this setup. Where is this area? So this W is an area. Where does this area exist? Between which axis and the curve? Lambda, it's this area right here. Now, from calculus, we learned that's problematic, isn't it? I got inverse functions and stuff as ugly stuff, especially if I have multiple windings. If I get multiple windings, this thing ends up being a beast. I got matrices, I got to invert them, I got all kinds of ugly stuff going on. This here, this area is the energy. All right, so what I call WFLD, like that. So I'm going to define something new. This area, which based on the title of my slide, maybe you can guess what it is. It's the co-energy. Is co-energy a real thing? No, it's not. It's just something I made up. I mean, I didn't make it up, right? But it's just a concept. All right. And I write it like that. W field prime. Okay. It's super easy to compute because it's basically the exact same thing as the energy for most systems. It's just a heck of a lot easier to deal with taking its derivative than it is to take the derivative of the energy. Okay. For reasons that I don't want to get into because they're ugly. Okay. So if I look at this guy, I can see one thing here. I can see that just real simple. We got lots of math, lots of symbols, lots of stuff, but let's just think about something that you could have thought about when you were in the 5th grade, right? Which is to say what did I draw? I drew a square, right? What's the area of that square? So what's the area of that square? Well, this side has I. That guy's got lambda. Yeah. So basically, I'm going to say I got lambda times I is equal to the sum of the area of those two triangles, right? That's this. W field plus W field prime. Okay. Try to follow all the mathematical details. You can get lost fast. You guys with me? All right. It's just a 5th grade statement here, right? Basically say that the sum of the area is equal to the area of that square is equal to the sum of the area of the two triangles that make up the square. Okay. So, all right, I got to use that. So I have lambda I equals, bless you. I'm late on that. All right. I want to take the derivative of that with respect to time. Why? Because I do. Because it relates to my power relationship. Okay. So if I take the derivative of both sides with respect to time, the easy part is this one. D energy dt. What's d energy by dt? Power. Okay. What's d co-energy by dt? I don't know. Co-power. I don't know. All right. What about the other side? So d lambda I by dt. I had to do the product rule, right? So that would be lambda times what? Di by dt plus I times d lambda by dt. All right. Now, we wrote down the first law of thermodynamics as V times I, or I d lambda by dt, is equal to d energy stored in the field by dt plus force times dx by dt. All right, we wrote that down. Okay, now let's just stop. We got lots of math, getting ugly. All right. So what does that bottom line say again? Tell me in words, what does that bottom line say? It's not that complicated. It looks complicated, but it's not. See, I already lost you. What's the bottom line say?
Power.
The power going in. So this is the power going in. Power in. Yes, power in is equal to and I'm assuming that some of the power, let me write this one. Instead of power, I'm going to say rate energy stored in field. I got some memory issues here. Okay.
That's real power.
Yeah, not there's no imaginary power to this. It's saying that if I have basically saying if that thing can move, then I can change the amount of energy stored in the system. And that's basically why that comes into play, right? So it's saying the energy I'm putting in at any given instant is equal to the rate of change of energy stored in the field plus the rate at which power is coming out. All right. So what do? I basically take these two things and combine them, right? I solve for this in terms of all this other stuff. All right. And I end up with some result. We're just going to jump to the result. We're not going to do the math on the many steps of that in the derivation. And I'm going to end up with this statement. I'm going to end up with the rate of change of co-energy equals lambda di by dt plus f times dx by dt. Okay, like that. Now, if I get rid, I can get rid of the d by dt. So basically, I get this. Basically, the dt's can go away, and I get lambda di plus f dx. Okay, now, you don't remember this. I know you don't remember this, but somewhere in Calc 3 or 4 or someplace like that, right? Basically, there's a statement also that I can write a total derivative in terms of partial derivatives, okay? Which is to say that I can write this as with x. What does it mean when I write a bar like that with x? What's that mean? Yeah, evaluated at that point. So x is a constant in that partial derivative. All right, and this is, and I'm about to get to the point of all of this. The other variable is held constant in this guy, and the variable is I. Okay, the variable is I. So here's where I end up with in this whole thing. If I compare those two relationships, they have to be equal to each other, right? They're the same thing. Right? It's complicated, but they're the same thing. It tells me that the force, and this is the bottom line of the whole thing. If you never remember anything I just did, this is the one thing to remember now. What's this tell me the force has to be equal to? Partial derivative. So these two terms here have to be equal to each other. Partial F, or F is the partial derivative of the co-energy by dx with I constant. It turns out the force is also equal to the negative partial derivative of the energy with the flux held constant. For reasons that we won't get into, that's an ugly, 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 ugly thing to do in a lot of ways. Okay. This guy's not. So that means I need to know how to calculate whatever the heck this co-energy is, which we can talk about real quick based on this picture, right? If I have, just for this picture, lambda equals Li, right? So if lambda equals Li, for your favorite materials that you have, what is the energy? It's 1/2 Li squared, right? So if I look at this thing right here, energy is 1/2 Li squared, lambda I is equal to energy plus co-energy. If I put those together, right, what do I end up finding out? Well, I end up finding out that the co-energy is 1/2 Li squared as well. If I put them together, everything works out. Okay, 1/2 Li squared is what I get for the co-energy. Okay, all right. So long story that we went through there, but I basically have this. So my co-energy is equal to 1/2 L of X I squared. And the force is equal to the derivative of that thing with I held constant. All right. So this again ends up being useful if I'm talking about something complicated like this guy that's got 3 phases. Okay. All right. My relay, it wouldn't really matter that much. So back to my relay. All right, back to my relay. For my relay, I had L of X, which is what? What's L of X again? Just make sure you guys haven't totally fallen asleep. What's L of X? It's the inductance as a function of position. Okay. All right. So there's at least 2 people that are still awake. All right. L of X is mu naught L times D minus X times N squared over 2G. Okay. The co-energy is what? What did I say that was? 1/2, yeah. 1/2 L of X I squared. So that becomes, in terms of, if I plug in my L of X, then it's basically mu naught L D minus X N squared over 2G. 4G. Right, because of the 1/2. All right, now I want to calculate the force on this thing. How would I do that? Well, I just said the force. Well, so the force is the derivative of the co-energy with I held constant. Or it's the derivative with respect to the position. So help me out. This guy looked complicated. Yeah, there's an I squared there. Thank you. So how do I take the derivative of that co-energy with respect to position? Yeah, so derivative with respect to X. So you guys don't like this because there's lots of symbols, right? But what do I know about mu naught? It's constant. What do I know about L? It's constant. Everything's constant except for what? X. What's the derivative of negative X? -1. So it ends up being basically negative mu naught L n squared over 4g times I squared. Like that. The d went away, right? What's that tell me about this thing? What's it going to do? Doesn't depend on distance. It tells me there's a force that's applied in the negative x direction, right? And so what's it going to do? It's going to yank him in exactly like we said it was going to do. It's going to try to pull that down, right? It's going to try to pull that guy closed. So if I look at what that's ultimately going to do, right? So the reluctance we said of the gap was G over mu naught L D minus X, like that. What's that guy doing eventually? What's that do to the reluctance? What happens to this guy eventually? What happens to this area? Yeah, be D minus D eventually. So what's it doing? It's trying to get the reluctance to be what? It's trying to get the reluctance to be maximized, right? It's trying to maximize the reluctance of the setup. Okay. All right. So this is our basic approach. If I look at what's happening, right? And that gets us to sort of a problem like this one, right? This is what you have in problem 5, which I'm asking you to kind of conceptualize. What do you think is going to happen? I'm going to put a current into that thing. What's the current going to do? It's going to try to align. It's going to try to pull it in. Okay. Now, this is an ugly drawing here. It's written in radians. It's saying that this right here, the reference, this is theta equal to 0. All right. And it's saying this guy right here is theta equal to 45 degrees. So positive theta is that way. All right. Now in this system, it's real similar. Instead of dx, what do I have? D theta, and that's equal to torque. And when we talk about motors, we most exclusively talk about torque rather than force, right? But we start out with force because it's easier to think about. All right. What do you think is going to happen in this particular case? What is going to happen in this case? He's going to move, and he's going to move until he gets to where? Until he lines up, until he gets to 45 degrees. All right. He's going to move until he gets to 45 degrees. So if I look at this particular case, there's 2 positions at which this guy could basically move to, right? One of them would be 45 degrees, right? That would basically be if this tip right here moved to 45 degrees. What's the other possibility? It could go all the way around to what? 45 plus 180 degrees. 225, right? So there's 2 positions at which this guy could basically be maximized, or two positions at which this guy will get pulled to, right? It all depends on like what I have right here. It's like this guy had 3 spots that he was happy to go to, right? He had one over here, and he had one over here. All right. So basically it's to say that in this case, there'd basically be 3 positions where this guy would be. Now, what I end up doing is if I were to draw a magnetic circuit for this thing, what would the magnetic circuit look like? Well, there turns out to be 2 MMF sources, right? I mean, I can put them there in series with each other, n over 2 times I and n over 2 times I. If the material here is got infinite permeability, which I tell you that it does, how many reluctances do I have? There's 2 reluctances in the circuit. The reluctance of the core would be 0. There basically is one of this space up here and that space right there, right? There's 2 reluctances in that setup. And those reluctances are both a function of angle, right? Reluctance top as a function of angle. and the reluctance bottom is a function of angle. And what I ask you to do is to think through, okay, where are those reluctances minimized and maximized? And how does that relate to the inductance? How does L relate to the inductance? Or how does L relate to the reluctance? How does that relate? N squared over the reluctance. So where the reluctance is minimum, the inductance is maximum, all that kind of stuff, right? And so if I wanted to calculate the energy in this thing, I would end up saying the energy or the co-energy both end up being 1/2 L I squared. And I give you a formula for what the L is going to be, and I ask you to kind of rationalize the formula that I gave to you in that problem. So this is more of a conceptual one, but the basic idea is there. So we did a lot of stuff, but basically there it is right there. Right? These are our two key results. I put those together and I can understand pretty much anything from this point forward. All right. So we're gonna use those in some other cases as we go. All right. So that's it for today.
So I admit that's 0. Where does that split? The two magnet fit, or these all these things? There's lots of magnets. Yeah. And so the axial flux machine. These guys create flux that goes over into this material. Or it's the toroid, and there's basically an A-phase one, B-phase one. This is a very complicated sort of machine. Yeah, it's relatively an axial flux is relatively and I don't know, maybe making it nowadays. Common is permanent magnet. It's called permanent. So this is a permanent magnet. We got pretty close winding, and then I have magnets on the root of it. Okay. Did you round that parking? So it was part of it this way. No, which direction it's gonna go. Right. So if I plug it in. It's got spot where happy. Around the expression. It depends on something else called the number of poles, which is something we haven't talked about. Yeah, the number of poles. It actually has 6 spots. That should, which is the part that's a little bit odd for people to think about. Yeah, you can turn it off. Yep, see it.
Hey, you guys see? How much time are you doing that?
Got a little bit, what's up?
Also, did you record today? I don't know if you did or not.
I did,
Okay,
I'm still recording, actually.
okay. I guess I'll be in the video.
You will be.
Hi, YouTube.